All right, let's look at some new identities today. We're going to look at something called the double angle identities. I'm splitting this into two parts because this section does get a little bit long. The focus of this first video will be algebraic manipulation. The focus of the second video will be solving equations. So, here are the two most basic. Sine of 2 times a, so sine of 2 times something will be 2 times the sine of a times the cosine of a. So if I know the sine of a and the cosine of a, I can know what the sine of an angle twice as big is. That's what this means. Similarly, if I know the cosine of a and the sine of a, I can know the cosine of something twice as big by squaring both and subtracting them. Now, there's actually two equivalent forms for this that come from our Pythagorean identities. And where we get them is by doing a substitution. What does cosine squared a equal? What does that equal? What could I replace that with? Well, I could replace that with 1 minus sine squared a. And then minus sine squared a. So 1 minus sine squared a becomes 1 minus 2 sine squared a. And if I were to replace the sine instead of the cosine with my Pythagorean identity, I could get this third version of the double angle identity for cosine. So there are three versions of the double angle for cosine, and it depends on the information that you're given in the problem. If you know cosine, you don't know sine, this would be the most appropriate. If you knew sine of an angle, but didn't know the others, this would be the most appropriate. If you knew both, we could use this first one. Now, there's a double angle identity for tangent also. It comes from simply taking sine divided by cosine. And we can use any of these to derive this, but what it is would be this. 2 tangent a minus, or divided by 1 minus tangent squared a. A is some angle. 2a is an angle twice as big. So we're going to use these to do some manipulations. So using cosine 30, show that sine of 15 is equal to that funny looking fraction. Okay, so 30 is twice as big as 15. I hope you know that. So what we can say is that cosine of 2 times 15 is equal to, and I'm going to use 1 minus sine squared x, or 1 minus 2 sine squared x. So 1 minus 2 sine squared of 15. That is the identity from the previous slide. Cosine 2a equals 1 minus 2 sine squared a. And now we happen to know what cosine of 30 is. The cosine of 30 degrees is the square root of 3 over 2. And we can now solve for the sine of 15. I'm actually going to move this over to this side and move that over here. So we have 2 sine squared 15 equals 1 minus square root 3 over 2. And I'm going to get a common denominator now. So 1 is the same thing as 2 over 2, So 2 sine squared theta, or sine squared 15, equals 2 minus square root 3 over 2. Now we can divide both sides by 2. We get sine squared 15 equals 2 minus square root 3 over 4. And we square root both sides. Sine of 15 equals the square root of 2 minus the square root of 3 over 4. And you might be saying, but wait a minute, Mr. Schneck, you just square rooted both sides. You were solving. Shouldn't you have a plus or minus there? And my answer to you is absolutely not, because 15 degrees is a quadrant 1 angle, and the sine of quadrant 1 angles are all positive. So I have just shown that the sine of 15 is equal to this square root 2 minus square root 3 all over 4 exactly. So what these identities allow us to do is find exact values for angles other than what's on the unit circle. Next example. Find an expression for cosine 4x in terms of cosine 2x. So this is actually a double angle problem, because cosine 4x is cosine 2 times 2x. So this 2x, this thing right here, that's like the a in our identity. And one of those identities involved cosine, didn't it? The identity that involved cosine is 2 cosine squared. 2 cosine squared a, so 2 cosine squared 2x minus 1. And we have just completed the task that was asked of us. We have now figured out that cosine 4x, so a cosine of something 4 times as big of an angle will be 2 times cosine squared of something twice as big as x minus 1. And that leads into the second question, and find an expression for cosine 4x in terms of just plain, ordinary, boring cosine x. Well, we just figured out that cosine 4x was equal to 2 cosine squared 2x minus 1. Now, let me take and write this squared a little bit different. It's going to make this problem much more manageable. I'm going to write it like this. Now, what can I replace cosine 2x with? Well, we just saw that. We just used that. I'm going to say that this is 2 times something squared minus 1. What's that thing going to be squared? Well, go back to your identity for cosine 2x. Cosine 2x is 2 cosine squared x minus 1. And we can expand and then combine like terms. If we want, or we have satisfied the requirement of the problem. It doesn't say to simplify. I would recommend leaving it just like this. But we could take this part here and write it as 2 cosine squared x minus 1 times itself, FOIL, then distribute the 2 and combine all the like terms, and we'll get an expression that has a cosine to the 4th power in it. And we could write it that way also, but that is unnecessary. It's not something that's essential for this problem. Now, you might be asking yourself, well, how do I remember these identities? That list is long, that list is icky, that I can't memorize that. And the good thing is, ladies and gentlemen, in IB, remember, you do get a formula packet. If you were to look at that formula packet under trigonometry, you will actually see these identities listed for you, which means you don't have to remember these, and I wouldn't waste my time trying to memorize these. You just need to remember that they're there and how to use them while you're looking at them. And that takes us to the end of part 1. I hope you enjoyed yourself as much as I did.